Our next set of lessons is about the intermediate value theorem. And before I talk specifically about the intermediate value theorem, I want to talk to you just generally about what value theorems are. So value theorems are basically used to prove or guarantee that a function will have some particular output value. There are 3 of them in total, and this is the first one. So if you're ever reading a problem and it's asking you to prove that a function has some value, like, oh, prove that f of x is equal to 15, or, show whether or not f of x is equal to 13 somewhere on this interval, it's indicating that you're going to need to use one of the value theorems. And like I said, the intermediate value theorem is the first one we'll be talking about. What it says in basic English is that if you have a continuous function that starts at some value, and I'm going to try and sort of draw this for you. So suppose you've got a function that starts with a value of f of a. Now what do I mean by that? Think about what the word value means, right? If a function has a value, that means that's its output. And in particular, when I say f of a, that means somebody plugged in a. It means the x-coordinate was a, and what they got back was f of a, right? So your function starts there. And then if your function ends at f of b, so let's say over here, there's, this value here, f of b, right? So all I know is that the function started here and ended here. If it's continuous, what does it mean if the function is continuous? It means it has no holes or jumps or asymptotes. What the intermediate value theorem says in English is that the function has to output every single value between f of a and f of b. There can be no missing values, right? And so, you just sort of imagine, how many different graphs could you draw between here and here? There are tons of them. You could just go straight down. You could drop down and then come back up. You could go up and then come back down. You could sort of, squiggle through this area. But what's important is that every single one of those graphs that I just drew, what you'll notice is every single height between here and here was hit. And so, just as an example, suppose that f of b was 1 and f of a was 7. That means this function has to have output 2 and 3 and pi and 4 and 5 and 6 and 6.7 and 6.8. It has to output all those values at least once for an input between a and b. That's what the intermediate value theorem says. So there's also a statement in formal mathematics, and it's important for us to know this as well. First, there are 2 requirements. The first requirement is that the function be continuous on the closed interval from a to b. Right? By the way, the closed interval from a to b, like this notation here, effectively means all numbers between a and b, including a and b. It's closed because it includes those endpoints, right? So that's the first requirement. It's a continuous function on the interval. The second requirement is that k be between f of a and f of b. And a lot of people get confused here because they're like, what the heck is k? K is basically our desired output value. Right? Remember that I said that the value theorems were all about proving or demonstrating the function has some value. K is that value that you want the function to have. So if those 2 things are true, then the conclusion, there is at least one c on the interval from a to b. By the way, this is now an open interval. It does not include a and b. There's at least one c such that f of c equals k. Now again, what does that mean? Right? C is basically the input that gives the output of k, right? So what the problem is saying is if k is in the right range, if k is between your output values, then there must be some input value between a and b that will give you that output value. That's how you will guarantee that the function has that value. So I have one example of this here that you might have actually seen from math analysis, right? And in fact, I know that this is one of the topics that's covered. So I want you to explain why this function has to have a 0 between 0 and 1. And remember that what it means for a function to have a 0 is that the function is equal to 0 somewhere between 0 and 1. Right? So how are we going to prove that? We're basically going to prove that using the intermediate value theorem. Right? The first requirement of the mean value theorem is that it be continuous. So how do I know how do I know that f of x is continuous? Right? Well, I know f of x is continuous because it doesn't have holes or asymptotes or jumps. It doesn't have division by 0, and it's not piecewise. So there we go. I mean, in your assignment, if you were asked to show this, you need to explain. So I'm going to write the function is continuous, and it's a complete sentence, because it doesn't have division by 0, and it doesn't have a piecewise jump between 0 and 1. That should be or. There we go, fix my typo there. So now the second requirement. The second requirement is that we want to show that our desired value, 0, has to be in between f of 1 and f of 0. And I didn't use less than or greater than symbols there because these two things might actually be switched. So all I'm going to do is I'm going to compute the two of them and find out. So when I compute f of 0, when I evaluate f of x for 0, I end up with f of 0 being 1. Right? Now f of 1, I end up with f of 1 being 1 plus 1 minus 4 plus 1. That means that f of 1 is negative 1. And so is this enough? Right? Well, it is. Our function was continuous. And the second thing, our desired value of 0 was in between 1 and negative 1. And so now we just sort of need to write this out. So I'll write out my conclusion, and then we'll talk about it. So if we want to write our answer formally and completely, this is what we say. Right? Because the function is continuous on the interval, because 0 is between f of 0 and f of 1, the intermediate value theorem does guarantee that f of x must be 0 for some x on the interval between 0 and 1. What I did in that sentence was I basically restated the two requirements, the continuity and the value being between the others, and then I gave the conclusion. The intermediate value theorem does guarantee that the function will equal 0. This is how we fully and completely justify our answers. I know some of you don't like writing complete sentences, but when we get to the AP exam and the IB exam as well, they want to see justification. They don't want to just see it, a bunch of messy work and then, yes, it is. We need to get used to giving answers like this. So another example, very, very similar. If you didn't pause the video and do the last one on your own, definitely do that for this one. Right? So for this one, we check for continuity first. So is this continuous? Yep. And I'll just put a check mark here because I know that I'm going to really fully justify my answer later. This is just my way of saying, hey, I thought about continuity. There was no division by 0, there's no piecewise, so I'm good. The second requirement, I need to look at whether 17 is in between f of 10 and f of 1. Right, so I'll compute these. What is f of 1? F of 1 will be 1 minus 5 plus 2. That means that f of 1 is, let's see here, negative 2. And then f of 10 will be 1,000 minus 50 plus 2. That means f of 10 is 952. Right? And so, we now look at the 17, we see it's definitely between the negative 2 and the 952. So now that we've done this little bit of scratch work, we can now write our nice answer. Again, I'd like you, if you haven't already done so, make sure you've got the video paused, make sure that you're writing down what your formal statement is, and see how similar it is to mine. So here's my formal statement of justification. The function is continuous on the interval, because there's no division by 0 piecewise jumps, and 17 is clearly between the two output values. Therefore, the intermediate value theorem does guarantee that the function will equal 17 for some x between 1 and 10. These are fairly straightforward examples of the intermediate value theorem. We're going to be getting into some things coming up where you sort of have to think a little bit more, so I'll see you there.